So within this lesson, we aim to understand what kinetic energy is, how to compute it, and in what units we measure kinetic energy. Towards the end of the video, we will have a real application on how to compute the kinetic energy of an object. All right, so first of all, anything that moves carries energy. For example, a car moving on a road with a given speed possesses energy because it's able to do work. It can crash into a wall, it can move something. Similarly, a ball rolling downhill also possesses a form of energy due to its motion. Also, something as simple as an apple falling down from a tree, that apple also possesses a form of energy related to its motion towards the ground. Now, here is where kinetic energy comes into play. We said that a moving object possesses an energy due to its motion. Well, that energy is what we call the kinetic energy of an object. So, for example, a stationary ball, meaning that a ball that is at rest, that is not moving, possesses no kinetic energy, while on the other hand, a ball that is moving throughout space, so let's say it's moving from point A to point B, we say that this ball is moving, it therefore has kinetic energy. Now, in order to compute kinetic energy has the following formula, where the kinetic energy of a particle of mass m measured in kilograms and velocity v measured in meters per second, the kinetic energy of the particle will equal half multiplied by the mass of the particle multiplied by the velocity or the speed squared. We notice that the kinetic energy of the particle is proportional to the square of the speed or the square of the velocity, meaning that if we double the velocity, the kinetic energy becomes 4 times larger than if it was the original velocity, which means that the kinetic energy is dominated by the speed rather than the mass of the object. However, that doesn't mean the mass doesn't contribute to the kinetic energy. So suppose you have one particle that has 1 kilogram of mass, and another particle which is larger that has a mass of 3 kilograms, and they are both traveling at the same speed of 1 meters per second. To the right, for example, it is completely obvious that the kinetic energy of the bigger ball, or the ball that has a greater mass, will obviously be greater. So objects with having different mass but traveling at the same velocity obviously will have different kinetic energies. Now, in the international system of units, the kinetic energy of a particle is measured in a unit called joules, which is abbreviated as capital J, where 1 joule is equal to 1 kilogram multiplied by meters squared divided by seconds squared. Now, as we discussed before, we said that a point particle of mass m traveling at velocity v, the kinetic energy of such a particle will be half mv squared, and that will be measured in joules. But now suppose that we have a rigid body that is traveling, that has a mass capital M and is traveling with a velocity v. How do we compute the kinetic energy of a rigid body? We know that a rigid body will be made out of teeny tiny particles that make up the object itself. You can say it's made up of atoms or molecules, or even particles, macroscopic particles that are within the object itself. Well, each of these little teeny tiny particles have their own kinetic energies that we can measure. So suppose each teeny tiny particle has a mass m tiny m, and let's say this is the ith particle, it has mass mi, and so the kinetic energy of the entire rigid body will be equal to the sum of the kinetic energy of its constituent particles. So we sum up overall the kinetic energies of all of the particles. We get to the point where we say, well, the first particle has mass, let's say m1, and is traveling at a velocity v, which is the velocity of the rigid body, because the entire body is traveling at the same velocity. Similarly, we can say that the second particle has the following kinetic energy, and so on. Now notice, all of the kinetic energies have two terms in common, so we can take the half and the v squared as a common factor of addition, and we can write it as a sum of all of the different masses that form up the rigid body. And so we can say that, well, notice that this term simplifies into the mass of the object, because the mass of the object is equal to the sum of the masses of its constituent parts, which means that the kinetic energy of a rigid body is simply that of a point object having this a mass capital M multiplied by the velocity squared. Or so now we're going to solve the following application in order to understand how we compute the kinetic energy of an object. So the question goes as follows. We have a car of mass m equals 1,000 kilograms, which is moving on a straight horizontal road with a speed v is equal to 20 meters per second. And the question wants us to calculate the kinetic energy of this car. So in order to do that, what we're going to do, we say that the mass of the car is equal to 1,000 kilograms, which is already in SI units. The velocity or the speed is in 20 meters per second, which is also in SI units. The kinetic energy of the particle is equal to half mv squared. We substitute the mass of the car, and we multiply by the velocity squared, 20 squared. We plug this into our calculator. We find that the answer is going to be 200,000 joules. Now I'd like you to try the same question, but doubling the velocity of the car, where the velocity becomes 40 meters per second. Would like you to compute the kinetic energy of the car and verify whether or not the kinetic energy is going to quadruple. It will be 4 times this kinetic energy. So within this lesson, we've learned that the kinetic energy of an object is the energy related to the motion of the object, and this is visible within the formula, which is dependent on the mass of the object and the square of its velocity. So the kinetic energy is equal to half mv squared. We learned that the kinetic energy is measured in joules in the SI system. The kinetic energy of a particle or of an object strongly depends on its velocity. So if you double the velocity, your kinetic energy is going to quadruple. So it's going to be 4 times the original kinetic energy. And we've learned that whether we can treat rigid bodies as point particles in order to simplify our calculations within physical systems. Okay, so kinetic energy as a concept is very important in physics because you'll find it all over the place, whether it's mechanics, aerodynamics, fluid dynamics, electricity, whether you're studying the motion of planes, planetary motion, cause. It's all over the place. It's a very important quantity that's going to allow us to compute and predict the motion of different systems